When alpha's fired at a sheet of gold leaf, what happens in brief is some deflection and a little reflection at an angle large, indicating a nucleus of positive charge. At the centre of the atom, types of nucleons are 2. The proton's repulsion stops the alpha going through. Neutrons have mass, but the charge is naught, and in small atoms an equal NP ratio is sought. Each is 3 quarks, strongly bound up and down. Nucleons just have those 2, but there's 6 going round. Charm and strange in the top and bottom 2. The charges are the same, but the mass gets huge. The quarks have charge in multiples of a third, so for a baryon it'll add up to an integer word. Protons and neutrons are baryons, which shows to bind to each other is what 3 quarks shows. You'll find these songs are different because they tether a quark and an antiquark, 2 opposites together. We've talked about hadrons, but in matter there's more. To balance the charge, electrons settle the score. The electron is the first and the most common one, but in later generations there's the tau and the muon. When particles interact, some properties are conserved. Momentum is first, a particle can't just swerve. Strong force colour, red, green and blue, equals mc squared, so mass energy 2. Electromagnetic charge has to stay the same. If you start with normal, you can't end up with strange, and the number of leptons and baryons cannot change. Neutrinos get less attention than they deserve, but their low mass makes them harder to observe. To interactions they are always reserved, so the lepton number can be conserved. The main bosons will carry a force. Photons mediate electromagnetic, of course. The weak force is carried by WWZ, while mass comes from the Higgs field instead. The strong force sticks stuff together with the gluon. Gravitational force is carried by the graviton. However, that's just theoretical, so for now, I'm gone.